Hi everyone, I just wanted to make a quick video here going over another example of the squeeze theorem for Calculus 1. So the squeeze theorem as stated in the book is if you have some function f of x that's less than or equal to a function g of x that's less than or equal to some function h of x, when x is near some a, except possibly at a, and the limit as x grows to a of f of x equals the limit as x goes to a of h of x, they both equal some number L, then the limit of g of x as x goes to a equals that same number L. So I wanted to do an example. So considering the example, when we want to know the limit as x goes to 0 of this function right here, which we'll call r g of x, x squared times sine of pi over x. We see that there's a discontinuity at x equals 0 because we have an undefined sign there. So let's jump over to Desmos and let's graph that sine of pi over x. With any sine function, we know that it exists between values of y values of 1 and -1. So we're going to add those to the graph as well. So look here. So we have our sine of pi over x function in red with y equals 1 at the top and y equals -1 at the bottom. So you can see that those two lines confine the entire graph sine of pi over x. So another way that we can consider this is we know that -1 is less than or equal to sine of pi over x, which is less than or equal to x squared, or no, to 1, sorry. The next thing we want to do is let's multiply both or all three of those functions by x squared. So then we get, so it's like we were just scaling all of those values. So we're going to get -x squared is less than or equal to, and it's a positive, so we don't have to worry about changing the order of, or in the direction of the inequality. So we have -x squared is less than or equal to sine of pi over x, which is less than or equal to x squared. So let's jump back to the graph and let's add those changes in. Instead, let's graph the sine of the function x squared times sine of pi over x. Let's graph x squared, and let's graph -x squared. So, at least for this range, we can see that red curve, or x squared sine of pi over x, is confined in those two functions again, just like how it was before with y equals 1 and y equals -1. So those two functions, which we could consider our h of x as our y equals x squared, that right here, and then our f of x is our y equals -x squared. They sandwich in the function we care about, the y equals x squared sine of pi over x, our g of x function. So this allows us to, let's try and calculate the limit of both x squared and -x squared. So visually, we can see as we approach 0, for either y equals x squared or y equals -x squared, we go to 0. So jumping back to that, we know that the limit as x goes to 0 of x squared equals 0, but that also the limit as x goes to 0 of -x squared is 0. So by the squeeze theorem, now that we can say that both of those limits were the same, we can say that because of that, the limit as x goes to 0 of x squared sine of pi over x equals 0. So the important thing to note here is that we got this result because we were able to have some bound, so our y equals x squared and our negative x squared, and we're able to confine that function sine of pi over x, or x squared sine of pi over x, inside that. So we can say that then the limit as x goes to 0, so considering those two results we have, the limit as we go to 0 from either side, we see that we approach 0. So that limit has to exist because we've sandwiched the limit in by functions that grow faster and ones that grow slower to it, basically creating a function or finding a function f of x, which we said our f of x was negative x squared, and h of x squared, where these two functions contained all of the behavior of our g of x. So we said that the limit then for that g of x as x goes to 0 equals 0. So that's an example of using the squeeze theorem. If you have any other questions, please let me know, and I will go through them as well.